Hello everyone and welcome to the last video that's going to be covering Physics 30 material, and this covers the last unit of Physics 30, which is particle physics. Now this unit aims to show you some of the work in the groundbreaking field of physics, such as the standard model of particles, quantum electrodynamics, and using mediating particles as a way to describe the forces of the universe. Now, the first thing that we need to cover in this topic is the idea of fundamental forces, that in our universe there are four main fundamental forces that govern everything in the realm of physics. So here, the first fundamental force that we can see is gravity. So this one's very common. We all know how this works, is that it acts over an infinite distance. So no matter how far you go from an object, you'll still experience a force of gravity from it, even though it may be minuscule or very small. And it affects larger objects to a greater extent. So for example, you don't emit that much force of gravity, however the sun keeps all the earth and the moon and everything in place in orbit. And so in particle physics, they aim to describe all these forces through something called mediating particles. And so in the standard model of particles, the particle that they use to describe the force of gravity is something called a graviton. Now, this particle has not actually been discovered yet or been confirmed. However, we still say in the standard model that this exists as a mediating particle. And so people right now in the contemporary age are still aiming to discover this and trying to prove that gravity can be described using the quantum theory of particles. So the next fundamental force that we're going to look at is the electromagnetic force. And as we know from our experience with electricity and magnetism, and light, is that this force acts over an infinite distance. So this is basically just light, and we know that the particle for light, we call it, is a photon. So this force is really simple again, and along with this and gravity, they both act over an infinite distance. However, the next two fundamental forces that we're going to look at, the weak nuclear and the strong nuclear forces, do not act over an infinite distance as the electromagnetic force and gravity do. So we're going to look at them next. So the third fundamental force that we're going to look at is the weak nuclear force, and this is the force that's responsible for most of the particle decay that we saw in the last chapter in nuclear physics. So some things such as beta decay, where you saw, well, how does that neutron turn into a proton, or how does that proton turn back into a neutron, and why is there neutrinos that are being emitted? Well, that's what we see here, is that the mediating particles that we see for the weak nuclear force, which are called the W and the Z bosons, there are the particles that are actually responsible for that change, and they're responsible for making those quarks inside those particles flip up or flip down. And that we're going to see later in the standard model of particles, is that when we group these mediating particles with real life particles, then it will create a new theory that will allow us to truly grasp the forces of the universe. And one important thing to note about this force is that it needs to have a certain range for it to activate the actual proton or the neutron. So you can't just change a proton or a neutron from miles and miles away. It has to be very, very close to the nucleus, which is why we see this interchange of the weak nuclear force only occur in instances of nuclear decay. Finally, the fourth and strongest fundamental force of the universe is the strong nuclear force, and this is the force that's responsible for holding together the quarks that exist inside protons and neutrons to make sure they don't break apart. So we see that this force is mediated by a particle called a gluon. And so in between all these quarks, let's say in a proton or a neutron, you have these little gluons that are holding those quarks together. And what's really interesting about these particles is that you can never actually really separate them from their carrier protons or neutrons, because if you try to separate these gluons or these quarks from the actual proton or neutron, then the energy required to actually separate that will be the same as the required energy to make a new one of those quarks or gluons. So that again obeys Einstein's mass energy equivalence that we see throughout the whole universe, is that you take one of these out, it requires energy. However, that required energy will just make another one of these quarks or gluons that holds it together. So we can never actually really separate, we can never make a proton or a neutron with two quarks, let's say. That's going to be impossible for us. That will be a new particle instead. And that we're also going to see all of these different particles when we put together the standard model that we're going to see next. So after we discovered the four fundamental forces of the universe and we started to look at particles more and more, we started to use accelerators to an even greater extent, and we started smashing together a bunch of atoms at even higher and higher and higher energies, and we started discovering more and more particles. So now we had all these particles, but we didn't know what to do with them. So we had to find a way to group them. And this was one of the beginnings of the Standard Model of Matter. So, for example, using particle accelerators, some of the types of particles we found were stuff like muons and pions, which are like electrons, but they have a lot more mass, and they have some nuanced differences that differentiate them both. Now, after that, so for example, we're talking about these groupings of the types of particles. We started putting them into certain groups that show their properties or their masses or stuff like that. So the first type of particle we have is a lepton, and it doesn't interact via the strong nuclear force. So this one does not rely on the strong nuclear force to keep together using gluons. The other type of particle that we discovered is a hadron. So this does interact via the strong nuclear force, so it does require the gluon. And there are subcategories of hadrons which are called mesons and baryons. So mesons have integer spin, so a spin of 1, 2, 3, 4, 5. And baryons have half integer spin, so that means 0.5, 1.5, 2.5, and so on. Now, this idea of spin is actually really complicated for our event in Physics 30. All we need to know right now is that spin refers to the rotational angular momentum of the subatomic particles, so how they spin basically on an axis. It's more complicated than that, but for the sake of Physics 30, we don't cover that in the curriculum. And now, after we learned of this thing called spin, is that the rotational angular momentum, we also saw that we could apply this idea of spin to just all particles, not hadrons in specific. So for all particles in general, fermions have half integer spin, and bosons have an integer spin of a whole number. And so that's some of the beginnings of the particle model of matter. And next we're going to look at the quarks that make up these particles. So the next advancement in the Standard Model of Matter happens to be in the realm of quarks. So now we discovered all these hadrons that interact via the strong nuclear force, so they're held together by these gluons. And so after we discovered these hadrons, humanity also discovered that inside these hadrons, they're composed of little particles called quarks. So that's what they said in the Standard Model of Matter, is that these quarks are what actually compose these hadrons. And so when we look at things like neutrons and protons, we found that they could be described by simply three quarks that are in different spins. So for example, the neutron has two quarks that are downspin and one quark that is upspin. And that can describe the neutron as a whole. And these quarks, again, we know are held together by gluons. However, this also led to a problem. There's a law in physics called the Pauli exclusion principle, which states that two or more identical fermions cannot occupy the same quantum state. So that means it would be impossible if these two quarks were the same for them to occupy the same state. That would be literally impossible according to the Pauli exclusion principle. So what this led to is even more differentiation between these quarks in this idea called quark colors. So you may have heard of this as well, is that each one of these three quarks can be described using one of the three primary colors. So they don't actually have that color. They're not actually red, green, and blue, but we say they're red, green, and blue to make sure they're differentiable by some means as to make sure they coexist with the Pauli exclusion principle. So that's another stride that we had in the quantum theory of matter that will also lead to great strides in the Standard Model of Matter that we'll look at next. So now that physicists had discovered all of these particles, all of these mediating particles, and all of these forces, they wanted a true and proper way to categorize all of these particles and these forces. And so here we have a simple version of the standard model of particles, in which we see a lot of the quarks, the leptons, and the mediating particles, which are the force carriers, all organized into one giant table. Now, even this is the simplistic version of the table because we have so many particles that we've discovered and so many generations of these particles that it would take so long to just fit them all into one table. And so these are just the simple ones that I'm going to discuss here. So up here, these six here, we see they're quarks. So they're types of hadrons, which means they interact via the strong nuclear force. And so here we know the up and down quark. So these two are partners. Heavier versions and more unstable versions of these quarks are the charm and the strange quarks. And even heavier and unstable versions of these are the top and bottom quarks. And so these are the quarks that we see inside protons, neutrons, and all of those types of particles. Now down here we have leptons, which do not interact via the strong nuclear force, so they're not held together by gluons or anything like that. And so here we see electrons, the electron, the muon, and a tau. And so these three generations of particles also have partners as similar to the quarks, which are their respective neutrino versions. And that just means they have an opposite charge to them. And then here we see all the way here are the force carriers, as we discussed before, which are the gluon, the photon, the W boson, and the Z boson. And those carry the forces, the four fundamental forces of the universe. Notice that we don't have the graviton on here yet, and that's because that's still a hypothetical particle. We haven't discovered it yet. And so now, in the contemporary age, we know that the standard model of particles is not enough to fulfill that need of uniting the fields of quantum mechanics and relativity. Right now, it's just not enough. We need something else, like superstring theory or higher dimensional analysis, to actually unite these forces and find a solution to the mysteries of the universe. And that's exactly what I'm going to show you next, is what are some of these questions in physics that we haven't answered yet, and how can we answer them potentially? Finally, we've reached the end of the Physics 30 curriculum. However, we know that there's still some big answers in the universe that haven't been answered by physics. So the biggest one of these is the idea of this unified field theory, is that how can we unite all these fundamental forces of the universe into one beautiful equation that truly describes all physical phenomena in the universe. So that includes stuff like the weak nuclear force, the strong nuclear force, the gravitational force, and the electromagnetic force. Right now, we can't unite all of them because on one side we have Einstein's relativity, which describes gravitational forces at the largest extents in stuff like black holes, planets, and stars. It describes that realm beautifully. On the other side, we have quantum mechanics using stuff like the strong nuclear and weak nuclear forces, which describes the realm of the atom very well and shows us those interactions in a very beautiful manner. However, we need a way to unite those two theories to describe every other missing piece in the realm of physics that we still have. And that's one of the biggest things that physicists are trying to solve in today's world. The next big unanswered question is this idea of the dark matter and dark energy in the universe. We still don't know what it is exactly. We still don't know why it's there and how it keeps on expanding our universe to such a great extent. We need to also know what this is. The last thing that's unanswered in the realm of physics is this idea of the multiverse theory. And this stems from the fact that there might be lots and lots of parallel universes that exist in a quantum state in the same realm as ours, but don't have a high probability of existing there due to, we know from quantum mechanics from the field theory. And because of that whole idea of probability and that whole idea of this multiverse. And so these big unanswered questions are all on the frontier of today's modern physics, and we're still trying to solve them step by step as we go. That's all for Physics 30. Thank you very much for watching.